Section 2.1 Matrix Operations, Math 26. So here is going to be not that of a difficult section today, but it's good to go through everything in case if students never learned matrices back in high school, then they will see it here. And for those who learn and forgot, it's a good chance to review this. So I already wrote down all the notes so we can save time. So if we are given a matrix A, okay, matrix A, we use A subscript ij, or A subscript I comma j, or some people use small a, to represent a matrix A, okay, a matrix A with I rows and j columns, I rows and j columns. So if you write A 3 2, that means it's a matrix A with 3 rows and 2 columns. And in general, matrix A can be written in this form: A11, A12 all the way to A1m, A21, A22 all the way A2m, and down all the way to AN1 all the way to ANM. So this is called how many rows? N by M matrix has n rows and m columns. And the entries on the A11, A22 all the way to MM or something, those are called this diagonal called the main diagonal of the matrix, and we call them AII. So like 1 1 2 2 3 3 all the way to MM or NN. So if we look at this example, this is called matrix A. This is 3 by 3 matrix. The main diagonal is this. These are the entries on the main diagonal. So this is called the main diagonal. 2 6 3. So the numbers inside are called entries, or element of the elements, but usually we call them entries. For square matrices, we call it n by n matrices. Those are square matrices. We have a special kind of square matrices. We call them identity matrices. A1, that's 1 by 1 matrix that comes only with one entry. A2, it's 1 0 0 1. The entries on the main diagonal are only ones, everywhere else zeros. For 3 by 3, the same way. Those are called identity matrices. Those are the matrices that come with main diagonal of 1 and everywhere else zeros. How do we perform operations with matrices? Perform operations means how do we add, subtract, and multiply matrices. So let's say we're given two matrices, one m by n and the other one m by n. We can define the sum of these two matrices by simply adding their entries, simply adding the first matrix plus the next one, and that can be done by adding their entries. So if I have something like this, I want to add these two matrices. Okay, so m by n matrices. This is 3 by 2 and this is 3 by 2. They have to be the same dimensions, same rows and columns to be able to add them. So the way you add them, you add the 2 plus -1. You got 1. 0 plus 3, 3. -1 plus 5, 4. 5 plus 1, 6. Then you do the 4 plus 6, 10. 6 plus 1, 7. And that's what I got. 1, 3, 4, 10, 6, 7. Next, if they ask us to find a multiple of a matrix, say 4a. 4a means 4 times a. The way you do this, you multiply 4 times the matrix A, and then how you do it, you multiply 4 by every entry. This 4 by this, 4 by this, 4 by this, by this, by this, and by this. So that gives us 8, 0, negative 4, 16, 20, 24. Matrices have some properties with their operations. First thing, if we take 3 matrices, call them A, B, C, with the same size means same rows and same columns, let r, small s be scalars. First one, if you add A plus B to B or B plus A, you get the same thing. That's called commutative property. If you add the first 2 matrices and add the answer to C, is the same as if you add B and C together, then the answer to A. That's called associative property. A plus 0 equals A. That's called additive identity. A is 0 here is a matrix 0. So the matrix 0 has 0 elements everywhere. The scalar times A plus B you can distribute because it's a scalar. R times A plus R times B. If you have a sum of scalars, R plus S times A, it's R times A plus S times A. That's called distributive property within matrices. If you have R times SA, you can multiply R by S first, then the answer by A. That's like associative property of multiplication. So this is saying if you multiply the first 2 together times A, is the same as if you multiply the last 2 together, and then the result get multiplied by R. So try the next one. A, matrix A and B are given, find A minus B. So all you have to do is subtract the entries, 1 minus negative 3. So A minus B, you can write as A plus negative B. So you keep A the same, plus multiply the entries in B with negative, and now it becomes addition, which is 4, negative 2, negative 4, negative 8, 3, negative 7. You don't have to do it, switch the negative to addition, but you can go straight forward into it. Try to find 2A plus 3B. 2A plus 3B. So 2 times the matrix A, I rewrote it, plus 3 times the matrix B. As a next step, you can multiply the 2 in with each entry and the 3 in with each entry. And then just add the entries across. 2 added with negative 9 is negative 7, 4 plus 12, 16, 6 plus 21, 27, and so on and so forth. Multiplying matrices, maybe I went over this couple of weeks ago, but we can repeat it here again. To multiply matrices, you need to, let's say you're multiplying m by n times n by t. The n's, they must match then to get m times t as a final answer. So the middle ones, they must match in order for us to be able to multiply matrices. And then what you get is the first one, first dimension, and the last one, n by t. So you get a new matrix C, and the way to multiply matrices, we multiply row by column, row by column. So if I need to multiply these 2 matrices, this is 2 by 2 matrix and this is 2 by 3. So the answer will be 2 by 3. So 2 by 3 matrix. How do you multiply them? You multiply row by column, this by this. 1 times negative 1 and plus 2 times 0. Then the same row by the next column. 1 times 1, 1. And 2 times 3, 6. Same row by the last column. 1 times 4, 4. 2 times 8, 16. We can do the same for the next row. Row by column. 3 by negative 1, negative 3. 4 by 0, 0. 3 by 1, 3. 4 by 3, 12. 3 by last column. 3 by 4, 12. And 4 by 8, 32. And then just simplify them. That's what I wrote here. And that will give us what we need. Negative 1, 7, 16. Negative 3, 15, 44. If you try to multiply it the other way around, try it. Try to multiply b times a. Let's see what you get. So if you try to multiply b times a, what happens is this is the first one is 2 rows by 3 columns, but this is 2 by 3. Notice 2 and 3 do not match, so you can't multiply them out. And if you try to multiply, you will face a challenge here. To multiply this row by this column, you multiply negative 1 by 1, and then 1 by 3. And how about the 4? You're going to multiply by what? Nothing. So it doesn't work out this way. So this tells us that here a times b does not equal b times a. In other words, matrix multiplication is not commutative. Only addition. Only in the addition works, but not in the multiplication. Try to multiply a by b here, and also do b times a. So multiply a by b and see what you get, and do b times a and see what you get for this example. So here we multiply a by b, as you can see, and I got that. Then b by a, and I got this. They are not the same. Doesn't mean we did something wrong. What means is just it means matrix multiplication is not commutative. Okay, matrix multiplication is not commutative. So what are the properties of matrix multiplication? First, associative is fine if you multiply the first two matrices and then the answer by the third, or if you multiply the last two and the answer by the first, it should work out. If you multiply a matrix A by the sum of two matrices, you can distribute it this way. You multiply A by matrix B plus matrix A by matrix C. If you do it from the left side or right side is the same. Just follow the order of multiplication. If we have a scalar r times ab, you can multiply r by ab or r by a then by b or r by b then by a. If you take any identity matrix multiplied by any matrix, you will get the matrix itself. If you multiply it from the right side or the left side, the identity matrix doesn't change the other matrix itself. Next one, how do we prove that A times BC is equal to AB times C? So how do we prove the matrix multiplication for the associative property for matrix multiplications? Let's start with this. So if we let matrix C with entries C1, C2 all the way to CP, those are kind of column. Then BC, when you multiply B times C, you multiply the rows of B by the columns of C. So we write it this way, BC1, BC2, all the way to BCP. And so when you multiply the A by BC, then you multiply A by the BC1, A by BC2, A by BCP. Then you can regroup the ABC1 as ABC1, ABC2, all the way to ABCP. And that's exactly the same as ABC. Like you multiply the AB by together, then the answer by C. It's important that you write that down. If you guys done copying, we can move on. Quick warnings: if AB equals 0, we cannot say A is 0 or B 0. You're not solving an actual algebraic equation. So if the product of two matrices is 0, doesn't mean either A is 0 or B 0. You can multiply two matrices and get the 0 matrix, but doesn't mean one of them has to be a 0 matrix. If AB equal AC, then it's not true that in general that B equals C. It's kind of like you cancel A and A. That only works if we have scalar. Next, AB does not always equal BA. How about powers of matrices? So if we take K to be any positive integer and a square matrix A, it must be square matrix. Then if I want to raise matrix A to K power, that means you're going to multiply this by itself K times. So someone's saying, can you give us an example of AB equals 0? You can come up with an example yourself if you like. You just pick any random entries on the first one and say -2, 1, like this. If you multiply this by this, you're going to get 0 for the first entry. And you can do the same for the other ones. So A to the K means you multiply A by itself K times the matrix A. By definition, A to the 0 is the identity matrix. I for identity. It's the one with ones on the main diagonals, everywhere else zeros. Then we're going to look at the transpose of a matrix. So what's the transpose? A to the T power is the notation for the transpose of matrix A. And how do you find that out? It can be done by switching rows and columns of A. So if you make rows of A to become columns and columns rows, the answer would be considered the A transpose. So if we look at this matrix, A, 2, 0, 4, 8, -1, 11. If I make the rows columns and columns rows, so the row 2, 4, -1 is going to become a column, and the same thing for the other one. That would give me A transpose. A transpose is the matrix that can be obtained by switching rows and columns, as you can see. If you do transpose again, so if you transpose the transpose, you'll get matrix A back. What are the properties of transpose matrices? Again, if you do double transpose, you will get matrix A back. If you add A plus B transpose, it's the same as if you transpose A, transpose B, and add them together. You'll get the same result. For any scalar R, RA transpose is the same as just transposing A, because the transpose does not affect the scalar. If you do AB transpose, then that would be B transpose A transpose, which is not the same as A transpose B transpose. Any questions up to this point? And you can show yourself examples if you like to see that. Say like I want to take A to be 1, 2, 3, 0, -1, 4, say, and B is, this is two rows by 3 columns. So make sure you have three rows here, 1, 1, or 1, 4, 1, 0, negative 1, 2, 3, 1, 4. This is 3 rows by 3 columns. So if you multiply A by B, you can multiply that, then find the transpose of the answer. Then compare this with, if you take B transpose, find it, A transpose, find it, then multiply B transpose, A transpose. You will see that property 4 will hold. Any questions about this?
Videos?
Yes. Yeah. How far? This far?
There is fun. Do you want us to solve?
Do you want what?
Do you want us to solve it with the transpose?
I mean, if I'm you, I would do it. Just so you can see it. Okay, so anyone has any questions about this?